Howdy, folks. It is March 25th, 2023. And I am excited today to talk to you about another random topic, but not so random because the topic has a great deal of interest for me. It's one of many things that has a great deal of interest to me, and we're going to be talking about cyclotrons today. Okay, so anybody familiar with antimatter? Yes, I'm going to talk about antimatter in a whole different video, but anybody's familiar with high energy physics, which antimatter, the study of antimatter and antimatter interactions and production fall under that category, should be familiar with the cyclotron. And most famous cyclotron in the world is the Large Hadron Collider, and there's many other cyclotrons all around the world that have a similar function. But cyclotrons are one of the most well-known and actually simplest ways to create to accelerate particles at very high speeds. And why would you want to accelerate particles at very high speeds? Because you want them to collide with other particles, and when particles collide with other particles at very high speeds, they tend to interact with each other because they can get close enough to each other because they surmount their energy repulsive energy boundaries, and thus things like the strong nuclear force essentially interact and cause them to break up in various different ways and form other fragmentary elementary particles. So typical particles which are accelerated. So now there's particle physics is predominantly interested in the field of high energy particle interactions, right? So you have protons colliding with other protons, protons colliding with electrons, electrons colliding with other electrons, colliding with other electrons, neutrons, etc. You have the whole gamut of elementary particles just being smashed into each other at the cost of billions of dollars per year in the name of science. And all this is important because you just like a little precursor to the cyclotron that I'm going to talk about is the idea of natural processes versus man-made processes. So in the 20th century is when advent and awareness of all of high energy physics became very prominent. People started understanding that because of quantum mechanics, because of quantum physics, because of general relativity, that there were forces in this universe much greater than was harnessable by mankind. And the forces that are surrounding us are typically you see a very powerful waterfall. And for you physicists out there or physics inclined people, this might be of marginal comparison to you. But let's say you look at the grandeur of a massive waterfall, Niagara Falls or something like that, where millions of tons of water is millions of gallons of water is literally crashing upon millions of tons of rock below, and the force is overwhelming enough to kill anybody. The same with volcanoes that lie on the plate boundaries between continental plates and cause massive volcanic eruptions. The power of the volcanoes is immense. The Earth itself has immense forces inside it, working within the core, bringing up massive amounts of huge plumes of lava called mantle plumes that essentially create entire islands on Earth, like the Hawaiian Islands. So these massive forces are working on scales unimaginable to human beings, but there are forces in the universe, as you know, for example, black hole collisions, black hole formation, black hole star collisions, star formation, star destruction, supernovae, things that are infinitely more powerful. As far as humans are concerned, they might as well be infinitely more powerful. Kind of just happening, and have been happening for pretty much eternity, or 13.1 billion years ago, whenever you think the Big Bang happened. So there's just been crazy events of like magnitudes that are just like on the scale of double-digit exponents occurring compared to what people experience. And so mankind can't harness these powers, and it's fascinating to know that they exist. But we can, in order to attempt to get close to harnessing these powers, we have to do things like create particle accelerators, where, of course, we can't slam two supermassive black holes into each other, or two stellar mass black holes into each other, which is far beyond the foreseeable future capability of man. We can't slam two stars together, which is far beyond the capability of man to see what happens. We can't even slam a planet into another planet to see what kind of crazy interactions happen there. So we have to settle for something smaller, like subatomic particles. We can't do that because they're so light, and because they, don't take, even they take high amounts of energy to accelerate to speeds at which they can interact and surmount each other's barriers to interaction. So back to the cyclotron. The cyclotron is a type of particle accelerator which is it's curved, so it's basically like a rounded. You've seen like these donut-shaped particle accelerators, like the toroidal one, the Large Hadron Collider, where you're sending, you're sending particles spinning and rotating, and as they spin and rotate through the diameter of the collider tube, they start off close to the center, and as they get farther and farther out, they gain more and more velocity because essentially they have room to gain more velocity. So you can given the power of these things, like in the fact that they're circular is how they're attaining these velocities. So there are things called linear accelerators as well. So those are not called cyclotrons; those are called linacs. And linacs are used to also accelerate particles. They're also used in other places where cyclotrons are not feasible to be used, but they don't have the ability to essentially, because one other way of thinking about it is that you can keep spinning. You can create additional distance through the use of a cycle that extends to its diameter. With a linac, in order to accelerate a particle to the velocities that you can in a cyclotron, you would need to, the length is impractical. You need to stretch out a linac like super far, and also you'd have to use different physics within the linac rather than the centripetal force of the particle around the cyclotron body to accelerate the particle fast enough such that it can interact with another particle. And you can imagine, because the space would be so large, it would be harder to control where the particle lands. So you have to make these particles collide with each other, right? And some of these collisions require precise control. So what I'm going to talk about a little bit is about the cyclotron's mechanics and how it works. So basically, what you have in a cyclotron, you have the cyclic part, which is the toroidal part, and you can have a cyclotron chamber. There can be several, but the basic configuration is that there is cylindrical or circular chamber, and the cyclotron's halves. If you slice the cyclotron into two pieces through the center, right, you'll get, I guess, a transverse cut would be called. You would get each half of the donut being called the D, right? Because I guess it's D-shaped, right? So DE. So the D is essentially, it's separated by a gap, and in this gap there is an electric field generator, an electric field that can switch, a linear electric field that can switch real quickly between positive and negative. So basically, this electric field is controlled by a voltage, an alternating voltage, right? And thus producing an alternating electric field. And the purpose of this alternating electric field I'll get to in a minute. But let's talk about components of the cyclotron first. So within the body of the D, each of the D's, right? Like the left D and the right D, you have magnetic fields. Okay, you have a linear magnetic field. So the magnetic field, the cyclotron works because essentially you're sending particles, right? So you're using charged particles typically in cyclotrons, and the magnetic field in your typical cyclotron is used to induce EMF, electromagnetic force, which by the law of induction, allows the particle to rotate, right? Because if you have a magnetic field, just go back to your Maxwell's equations. If you have a particle moving in a straight line, and there's a magnetic field next to that particle, the particle will be affected by the magnetic field, and the orientation of the particle will change. The velocity of the particle will change as it's moving through the magnetic field. It will essentially, if the magnetic flux, so you can use the right-hand rule and Faraday's law to kind of determine which direction the particle will travel in the magnetic field. Essentially, the magnetic fields are have linear components that permeate the body of the cyclotron D, and when the particle is first launched from its source, it travels along, and its rotation is affected by these magnetic fields, and it rotates and returns from one end of the D to the other end of the D, basically in the opposite direction. So remember, this is a charged particle, so let's talk about protons. There's different ways, different cyclotrons are set up with different structures for different types of particles, but let's talk about protons. So a proton is a positively charged particle. It travels to the right, and as it curves through the magnetic field, it travels in the opposite direction and then travels to the left. Once it hits the D at the left, what will happen is, now remember the electric field I talked about, and the variable electric field in the center between each D. The electric field now will have to switch polarity, or switch direction rather is a better way of saying it, to allow the proton to accelerate along the direction of the electric field, or electron, which would accelerate in the opposite direction. Because if the electric field did not change its direction, then the electric field would oppose the motion of the proton and cause it to stop. So basically, you'd be launching like baseballs in the form of protons from one end of the cyclotron to the other, and there wouldn't be any point, essentially. So you essentially have to cause the proton to rotate around the cyclotron. That's the whole point of the cyclotron. Now, the proton does not rotate once around the cyclotron. If the proton rotates from one semicircular part to the other, then the electric field switches in the middle, which causes the proton to travel through the length of the cyclotron midsection. And then once the proton travels through the length of the cyclotron midsection, then once the proton travels through the length of the cyclotron midsection, then it will go to the other side. Its polarity will be reversed, and it will cycle around again the magnetic field, perpendicular to the magnetic field in the second part of the D, and then it'll complete the second arc of transportation to the other end, the original starting end, the starting D, when it hits the starting D, the electric field will switch orientation again. And so this process happens as the proton travels through the cyclotron, and it keeps happening very fast, right? In order for now there is a controlled way, depending on the rate at which you want the proton, the rate of the speed at which you want the proton to travel and spiral through the cyclotron, because there is a spiraling. What happens, the cyclotron is designed so essentially the length of the proton's travel is increased because of the number of spirals it will take. If you wanted to complete more spiral legs, let's say faster, you need to change the frequency of alternation of the electric current in the center of the D of the cyclotron. Okay, so when you do that, this is called the cyclotron frequency. The cyclotron frequency is a factor of a number of things, but primarily it's a factor of the magnetic field strength, the mass of the particle in question, the velocity of the particle that you're trying. So basically, so this is one note I want to speak on here. Like, let's just say the magnetic field strength, the charge of the particle, and the mass of the particle for the basic cyclotron are the main components of the cyclotron frequency, right? So, if you tune the cyclotron to this particular frequency, the proton can travel happily along, and then you'll get a very fast proton, and then you can collide the proton into another proton, but we'll get into that later. But now, here's the kicker, so cyclotrons, one thing, this is the classical mechanism. If classical physics was the only kind of physics that needed to be taken into account, then this would be sufficient. But you don't have, in real physics, when something travels closer and closer to the speed of light, it undergoes relativistic effects, right? So if you're familiar with time dilation and length contraction, you'll know that relative to the medium that the object is traveling in, that object will experience a slower progression of time, called time dilation. It will become shorter in the direction of motion, which is called length contraction. And what that will end up doing, because there's a time dilatory effect, what will that end up doing? That will end up affecting the velocity of the particle. So if the velocity of the particle is altered, then the cyclotron frequency that was now originally a constant based on the magnetic field strength, the mass, and the charge of the particle will no longer be valid, because the magnetic field strength, because these are all constants, and the velocity has changed of the part, and these are all constants based on the velocity of the particle, the estimated velocity of the particle that it should travel in around the cyclotron, and in a classical sense, right? Once time no longer behaves in the same manner for the particle, the velocity changes, and you essentially have a contraction factor that is a multiple of the Lorentz factor, right? So the Lorentz factor is, as you know, who have taken general and who have taken special relativity, is what determines the length, the contraction, right? And so you have the rest mass, the difference between relativistic mass and rest mass. And while I'm mentioning relativistic mass, there's some controversy of what relativistic mass really is, but let's not go down that route. But you can get relativistic mass, right? Because the mass will change of the particle. That's the key thing. It's the velocity changes causes a change to the mass, the relativistic mass of the particle, which now the cyclotron frequency is dependent on the mass via the Lorentz factor, because that's in the denominator of the cyclotron frequency. And that Lorentz factor is called gamma, typically, is the root of 1 minus v square over c square, where c is the speed of light, and so v square is the speed of the particle in question, right? In its own frame. Okay, so we're not going to get too much into relativity here, because we can't. We were talking about cyclotrons and now synchrotrons. So synchrotrons and cyclosynchrotron or synchrocyclotrons are the answer to dealing with relativistic velocities, because in cyclotrons, this is a device which has a variable cyclotron frequency. So basically, as the particle travels closer and closer to the speed of light, the variation in parameters of the cyclotron frequency will change, but magnetic field could change. That's the primary variation component. The magnetic field will change to accommodate the synchrotron, right? And also so much So much so the frequency of the alternation of the electric field in the center of the cyclotron or synchrotron Ds will also have to change accordingly. It will have to essentially accommodate faster and faster transitions. So this is what is termed frequency contraction, because the frequency has to get essentially the frequency has to get is now affected in its denominator as the velocity increases. The Lorentz factor root becomes smaller and smaller, and then you're going to have to. This is increasing the frequency, increasing the magnitude of the numerator, and thus you're affecting the cyclotron frequency. So you're going to have to, as the particle traverses in a circular orbit of the cyclotron, it has to then change the frequency for each particle. Now this becomes more complicated when you start to take into account that the precision of a synchrotron as opposed to cyclotron there's much more precise equipment required in developing this device, right? And one can imagine that this is the case because, I mean, if you think about it, like, these things have to be tuned. In order to tune to relativistic changes in the particle mass, right? You're going to have to be very precise with the particle's motion, and as the particle reaches each point in the D again and again and again, it will require that you have a precisely tuned resonance for this synchrotron frequency. Okay, so that's basically just something to think about. I'm going to end it here because I just wanted to talk quickly about the different types of colliders. There's also many other kinds of colliders and other types of particle accelerators. We didn't actually get into the collision part, we just talked about the acceleration part. But we'll talk about collision later on. And I'm sure we'll get to my favorite topic, antimatter, pretty soon. And thanks for watching. Appreciate it.